Thank you for the invitation to present today. I'm going to talk about using internet reports to continually update predictive disease maps. And what I mean by disease maps is any map that shows geographical variation in disease risk, some metric of that. And by predictive disease maps, I mean maps that use mathematical models to fill the gaps in the data we have for disease risk. So here we have two examples. On the left is a prevalence map for Plasmodium falciparum malaria, and on the right is a probability of occurrence map, the one in the middle there, for dengue. And what I'm going to talk about today is mainly the ones on the right. So the prevalence maps are a fantastic resource, and we've seen them up in a few talks already today. However, prevalence modelling is very data hungry, and only a very small number of diseases have the volumes of prevalence data needed to map that metric. So a lot more diseases we actually have decent volumes of data on occurrence of the disease, and this modelling approach is slightly less data hungry too. So if we want to produce maps for a large range of diseases, which we do, and if we want to keep them up to date, then mapping the probability of occurrence is feasible. However, there are some limitations even with that approach. So down here we've got the process that we go through to produce just one of these maps, and it takes 2 to 3 years to do that. So we've mentioned the peer review process a bit already today, and if you're not publishing with RSTMH, then it might take a little while. And if a disease is changing rapidly, then you may find that the map is in danger of becoming out of date as soon as you publish it. Even if it's still fine when you publish, if you want to update it, you certainly don't want to wait 2 years for the next map and another 2 years for the one after that. So this project was designed to see if we could use novel sources of data and novel methods to continually update these kinds of maps. And our approach is here. So one of the first stages that we currently use in both map types is that we define the extent or the geographical limits of the disease. That's been done manually in the past. We've now built a system to largely automate that with expert opinions feeding in there as well. And then we spent a lot of time looking at novel sources of data, how we can capture those and how we can validate those and prepare them for use by a spatial model without the huge amounts of manual effort that we've had in the past. We've also done a small bit of work just to automate the modelling process itself. And then we are a map generated by the model is now going directly onto a website. So it's not going through that peer review and academic publication stage. However, peer review is very important, external opinions are very important, and we're largely talking about a process where the model development and so on will still be published in the academic literature, and the first map will be published there. But then the updates will be online much more rapidly. And although we're not going through peer review with the academic literature, we are getting in external validation in 2 different stages of this process. So the next change when we're going from producing a map to producing continually updated maps is that we're going from a linear process to a cycle. And this is a simplified version of the system we've built. And it's something that we've only just built, so we launched about 4 weeks ago. And I'm going to talk to you about this in some detail. And I'm going to start off by talking to you about the data that we use and how we process that and how that's used to generate disease extents before we go into the modelling process. So I'll talk about the first steps. And the very first step is the data that we're using. So traditionally, we've taken data from academic studies that are published in the literature, from Ministry of Health reports where the data has been checked at the level of district and then state and then centrally and comes through to us and we check it, so on and so forth. And these checks are a fantastic thing, but they take a very long time, and it means even when the data first reaches us, it can be a little out of date. So this is a screenshot from a website from HealthMap, which some of you may be familiar with. So what HealthMap do, rather than obtaining data from those traditional sources, they identify sources that are available online that are reporting outbreaks of diseases. And they're not going to the entire of the internet, so they're focusing their searches, and they identify sources such as ProMed Mail, and ProMed specifically release information about disease outbreaks. But they're also going more broadly to organisations like Google News. So Google News are obviously providing reports on every subject under the sun. but they're specifically looking for the disease outbreak data within that. Then, for example, Baidu provide a service that's a Chinese language news search engine. So we're not just limiting ourselves to English language or English, Spanish and French, we're trying to go broadly. So once HealthMap have identified those data sources online, and I'll call them feeds later in the talk, they then use text processing algorithms to identify the reports that contain a specific disease and a specific location, and they extract that data. So that's a fantastic resource, because what you can see on the screen here is 1 week's worth of HealthMap data for dengue alone. And in fact, this is last week, and we're getting a lot of dengue cases at the moment. It's fortuitous. So you can see these are decent volumes of data from just 1 week. And if you went and explored their site a little more, you'd see these are all current outbreaks. So we've suddenly gone from a situation where we might be receiving data a year after an outbreak in the field to now receiving it within a week, which is fantastic. So we've addressed the timeliness issue, but that comes with some disadvantages. This data hasn't been through the rounds of checks that we've had traditionally, and if we wanted to manually check all the data provided by HealthMap, we'd be straight back to square one. So we want to build processes that handle this kind of data. And there are two issues with this data before it can go through to one of our models. So the first issue, you can see in the USA here, there is a point which looks like it's exactly in the centre of the USA. And if you went to the HealthMap website and clicked on that point, it's an interactive map, and you would find that that point is representing the whole of the USA. So somewhere in the USA there's been a confirmed case of dengue, if this is a valid report. And it doesn't mean that that case of dengue happened exactly there in the middle of the States, or that there is any dengue there exactly in the middle of the USA. So for our spatial model, we can handle information that's linked to precise points, a town or a village, but we can also handle disease data that's linked to a polygon, so a country or a state or a district. But that's not provided by the HealthMap data. So the first thing that our process does is take their data, and we ingest it daily at midnight, and we classify all of their data as representing countries, states, districts, or a precise location. And then for those first three classes, we then match up their information with digital data we hold that describes the polygons that this data is linked to. So we have PostGIS data for all countries, states, and districts. So that's the first stage of the process. However, even when we do that, the information that dengue is somewhere as large as the USA isn't hugely useful for the model. And so we have a process of weighting that data. And if the data is linked to a precise location, if the outbreak is happening in a single town, that has a weighting of 1. If the area that the data is linked to is 115,000 kilometers squared, then that has a weighting of 0. And we're talking about the size of Honduras there. So anything larger than Honduras is actually, the data isn't going through to the model. And anything between 1 kilometre squared and 115,000 receives a weighting, so the larger areas get a lower weighting. So that's the first bit of work we do to turn this digital data into the kind of spatial digital data that we can use in modelling. The next question we have to address is, are any of these points actually valid? Is this real data here that hasn't been through the kind of checks that we like to rely on? And so we've built a process to handle that. And the process involves 2 parts. So in part we ask external experts to manually validate these points, and we've built an online system to make that easy. But we don't want external experts to have to validate all of this volume of data every single week. So we've also built a machine learning system that learns from the experts and starts validating the data itself. So I'm going to talk you through both of those things. First of all, the manual validation by disease experts. So by a disease expert, I mean it could be someone who knows a lot about this disease or a related group of diseases, so someone who knows a lot about dengue. Or it could be somebody who's based in a particular area, maybe Brazil, and they know a lot about the ranges of diseases in Brazil. So Anybody who's got a good idea about where a disease is occurring, and they don't have to know across the board, you can go on and just validate the things that you know about. And this site is now live. About 5 weeks ago it went live, so anyone can go to this address here. We ask you to register if you're validating data, but it's a very simple process, and you can then validate these data points. So if I very quickly take you through that process, you can see that we have a data point down there in Argentina. So you click on that, the map will zoom through and provide you with a bit more information about that data point to help you make your decision. And you may be sat in Argentina and you know very well there's an outbreak in this location right now, in which case you can make your decision straight away. I'm not sat in Argentina. I know that this is on the fringes of the distribution of dengue, so I want a little more information. And in the right-hand panel, you can see the disease is confirmed as dengue and the date is confirmed as the 20th of March, and that this point is referring to the province of Cordoba. So that's mentioned on the map there and in the panel to try and highlight the fact that it's not simply that spot on the map, it's talking about the province. And then on the right-hand panel, there's a little summary that comes from the original online data report, which you can translate into the language of your choice with Google Translate. Or if you want to see more detail, you can go directly through to that original online report. So if we do that now, this is it. So this actually came from Google News. It wasn't a high-quality ProMed feed. It was simply Google News. And you can have a read of the text and see that the Ministry of Health confirmed that there are dengue cases in the province of Cordoba. There's an outbreak right now. So with my knowledge of dengue and seeing that background information, I'm happy that this point is valid. So down in the bottom right of the screen, I have 3 choices. I can decide the point is valid, that it's unsure whether it's valid or not, or that it's invalid. And underneath that, you'll see a counter. If I hit the valid button, the point disappears and the counter goes to 2. So that's the experience that the disease expert has. And the volume of data that we're receiving for disease experts, you can do 5 or 10 minutes in a day, and you can validate all the points that we ask the experts to have a look at. So we've hoped to make it quick and easy. That's what happens at the front end. At the back end of the system, this is what happens. So when an expert validates a point, if they say it's valid, that gives it a score of 1. If they say it's unsure whether it's valid or not, that's a score of 0.5. And if they say it's invalid, that's a score of 0. Nice and simple, but this system is open to everybody. Anyone can register and use this, so we want some insurance in case someone registers who isn't quite the expert in dengue. And so what the system is doing continually with all of the experts is it's actually weighting the individuals, and this is information that's just in the system, this isn't shared anywhere, but it's weighting the individuals against each other. And we use that weighting to then decide which scores from which experts go through to the validation weighting that we attach to this data point. And so in this example, we chose a threshold of an expert weighting of 0.6. And you can see in the table in the bottom there that the top 4 experts, have ranked them, and the top 4 all had an expert weighting greater than 0.6. The bottom 2 didn't. So the top 4 scores went through, and an average of those is very simple. We just take an average. So we obtain a validation weighting of 0.875. So this goes through to the model together with the geographic weighting that I talked about earlier. So that's the system which the disease experts use to validate data. And that data now, that validation weighting linked to that data point, they can go through directly to the model, but they also go through to a training data set that we use for our machine learning process. So I'm going to spend a little bit of time on this slide. I've talked through how we obtain the pool of validation weightings from the expert. In addition to those validation weightings, every disease occurrence point that comes into the system is assigned 3 metrics, 3 values by the system. The first of those is for the feed. So I've talked a little bit about that already. So the feeds are things like ProMed, Google News, and so on. Then a value is also assigned for the probability of occurrence at the location that this data point is linked to from our most up-to-date map. So this is a cycle, and we'll come round to how we obtain this particular value in a few slides' time. Then the final value that we assign to every data point that comes in is the distance from the current disease extent that we have. So again, this is a cycle, and we use the current disease extent to calculate the distance that this data point, the location it's linked to, what distance that is from the current disease extent, inside or outside the extent. So we have 3 values linked to each data point, and they have a validation weighting from the experts. And that goes into the machine learning system, and we use a logistic regression to obtain a predictor, so that as new data comes in, we can then predict what validation weighting the disease experts would have assigned. But if we do that simply with one training data set, the issue we get is then we don't have an idea of the uncertainty in that value we get for the validation weighting. And we want to know that because we don't want to send the more uncertain values through to the model. So the way we get around that is we take the training data set and we subsample it randomly 6 times to obtain 6 training data sets, 6 individual ones, and the predictors are trained, so we get 6 predictors trained on 6 training data sets, and then for each data point that comes in, we then obtain 6 values for the validation weighting. If those 6 values are in agreement, and we simply use the coefficient of variation to determine that, then we take an average of those 6 values, and that's used as the validation weighting that goes to the model. If they're not in agreement, we actually have the option of going through this system 5 times. So this is a chain ensemble approach. So the 6 training data sets and predictors is the ensemble, and then the chain, we've got a chain of 5. And if by the end of that we haven't managed to achieve agreement on what the validation weighting is that should be assigned to this point, that point then goes through to the experts to review. So that point isn't lost, it receives a validation weighting from the experts, but not just that, that point then goes into the training data set. So the machine learning system has the chance to learn from that. And of course there are some sets of values that will inherently be variable and will always come through to the data, and we want to the experts. And we want that, we want them to consider those points. We want this system not only to pick up when there are changes to what's happening with the behaviour of the disease and how the experts have validated it. So to do that, we train the predictors, we retrain them from scratch every week. But not only that, we always want it to be current. We don't want to reflect the behaviour from a year ago or 2 years ago. So the training data set only uses data from the last 4 weeks. So it retrains every week using data from the last 4 weeks. So, going backwards. So now, with the combination of disease experts and with the machine learning system, we have a set of occurrence data that's been linked to location data the model can use, and it's validated. And we have geographic weightings and validation weightings that are linked to those data points. So that data is ready to go through and be modelled. And that data provides us with information about the presence of the disease. But the model we're using at the moment for the probability of occurrence is a niche or species distribution model that also requires some information about absence. And the way we currently provide that information to the model is using a disease extent. So I'll talk to you a little bit about how we generate these. So what you've got here is a disease extent that's been produced automatically in the system for Plasmodium falciparum malaria. The areas in dark purple are known presence of this particular disease, light purple possible presence of the disease. The yellow areas are uncertain, the light green are possible absence, and the dark green are known absence of the disease. And we obtain this extent through a combination of the data that's been validated that helps inform whether the disease is present in a particular area, and expert opinions. So I'm going to quickly talk you through now how we obtain the expert opinions on this map. And they're all important for a couple of reasons. So they help us to be confident about absence, which is hard to be confident with the presence data that we've got and with the biases in reporting in that data. So they provide us with the absence on this map. They also, because they do that, the presence data and the fact that we're generating maps, for example, on a weekly basis, mean that the system is quite good at picking up if the disease is expanding, if the extent is growing, but that system with the presence points alone isn't necessarily picking up the disease shrinking very well. So this process of experts providing opinions on this map is where we're most sensitive to shrinking borders of the disease. And an expert can choose to select a particular location on this map. So they might choose Tajikistan here, or they may use the table on the right to select Tajikistan. Clicking on either of those things zooms the map to the place you've chosen, and it also takes you in the table to that place. And in the table you can see how many validated occurrence points we have in our database for that country. So Tajikistan is 2. We also display in the table in the top right of the map a little bit of information about the 10 most recent occurrences in that country. And in fact, Tajikistan, there are only 2, and they're both in 2001. So the expert can then provide their opinion on whether in that particular area, in Tajikistan, the disease is present, uncertain, possibly absent, or absent. And they can also click I don't know, which is different from uncertain. So by uncertain, it means that it is genuinely uncertain whether the disease is in that area. So maybe they've been eliminating malaria, they've had no cases for a year, but you can't be absolutely certain they're malaria-free yet. So, which is different to this expert is actually in another part of the world and simply doesn't know. So it's a different thing handled differently by the system. So you then click on this, you'll notice the counter at the moment in the bottom right is on 0. You click on it and the counter goes up. What's more, Tajikistan in the map is now hashed out and it's disappeared from the list on the right. And we do this to enable people who want to go and validate or provide an expert opinion on a lot of polygons. They can go through and they know what they've done already. However, it's really important in this system that they can then go back and provide a different opinion next week, because the disease may change, their knowledge may have changed. So that hashing out and the disappearing from the list within 7 days, when the next disease extent is generated, that goes, and you can go back and provide a new opinion. So that's how we define the disease extent. So we're now in a position where when new data comes in, we've talked about it gets a value for the feed that it's come from. It also obtains a value for the distance from disease extent, and this is how we calculate it. So it's very simple. The system knows where that data point is. In this case, it's in Brazil, and it simply calculates the shortest distance to an area of possible presence or presence. And that's it. That's in kilometres, and that's one of the values that goes through to the machine learning process. So now we have validated data ready to go through to the model, and we have a disease extent made up from expert opinions and data also ready to go through to the model. So now I'm going to talk a little bit about the process of model runs and what happens next after that. So in order to trigger a model run, we have a couple of triggers. So the first one is based on an amount of time. And so rather than producing a new map every 2 years, we're now in a position where we can do this every week. In theory, we could do it in less time, but not many diseases are changing that rapidly. And we want a little time for the expert input to come into the system. But at the moment, we actually have diseases that are being updated every week. However, we also have, that doesn't need to be a week. For diseases that aren't really changing, that can be set as a month, 6 months, whatever's appropriate. So because we can have some longer lengths of time, we also have a trigger that's based on volume of data, and specifically volume of new locations. So if data is coming in at locations that we already hold, that's not adding to that trigger. But if we're getting new locations, then that can trigger a new map being generated early, before the length of time has elapsed. So what happens then? The trigger has occurred, whether it's by volume of data or whether it's from a time elapsed. The first thing that the system does is it needs to decide what data goes through to the model. And we want every map that we generate to be the best possible contemporary map that it can be. So we don't want to use all of our data going back to 1991, 1960, whatever it is, if we don't need to. So for every disease, we specify a minimum volume of data, and the system takes the most recent data point and goes back in time until it's achieved that volume of data, and then defines a cut-off date. So we're only using the most recent data that we possibly can in order to generate a robust map. However, if that's the only thing we did, we'd have a big problem with the sampling bias that you get with particularly all data really, but particularly these internet reports. There's a heavy bias to North America and Europe. You get a lot more reporting in the Americas than you do in Africa. So in calculating how far back through the input data the system goes, it also uses a measure of the spread of the data as well as the data volume. So the system goes back from the most recent data point in time until it reaches both thresholds for the minimum data volume and spread. It defines the cutoff, and then it uses the data from that cutoff to now to go into the model and to go into the latest disease extent together with the latest expert opinions that have been provided. And it's important to note that for all of these parameters, we're able to set these individually for each disease. We're also able to change them if the disease is changing in time. And for the threshold of new disease locations that we use to trigger a model run, we also have the ability to set a distance that they are outside the extent or a value of probability of occurrence they need to achieve before we want to trigger an early model run. So this has all happened, everything has been met, and the model runs. And this is an online atlas that's available online today, and this you don't have to register. So if you're going to be doing any validation, and we hope you will, and it would be much appreciated, but if you're not doing that, you don't need to register. This is open to the public. But before I talk about the online atlas, just to close that loop of that cycle of producing maps, I mentioned that every new disease point as it comes in is assigned a probability of occurrence at that location, and that comes from this map. So this is a map showing the probabilities of occurrence for every 5 by 5 kilometres in the world. So the latest map that's run, if a new data point comes in the next day, the probability of occurrence for the location of that data point comes from this map. So that's closing the loop. That's how we produce continually updated maps. We're quite a new project compared to the other ones you talked to today, so our volumes of data are quite low because we're only in the first 4 weeks, but we're already up and live and producing updated maps. So this is a dengue map, and you can see up here that when I took this screenshot there were 4. I think this morning there should be 5 of them. We also have New World cutaneous leishmaniasis up there, and we have a number of diseases that are going to be coming online throughout the year and next year. What you can obtain when you come to this atlas, you can visualize, zoom, pan around this dengue map, and you can also choose up here, rather than showing the risk map, you can choose to see the disease extent that was produced at the same time with that same contemporary data. And importantly, we do show you what the date range was of that data. So it's 2008, I think that says, to now is the data that's gone into that particular map. And we can adjust the settings as we achieve more data and we're happy with the modelling process. So for both the disease extent map and the disease risk map, you can download these maps as images, or you can download the data behind them. And that happens instantly just by clicking on these buttons. You can also obtain the input data that went into this map if you want to use that. No problem. And finally, if you're a little more interested in the modelling process itself, you can click on the bottom button here. And on the right, we have some model validation statistics, area under the curve and so on. And that's for this particular model run, for this particular disease. So they'll be different if we'd clicked on a map that was produced a week ago or 2 weeks ago. And on the left-hand side, you can see the top predictors or covariates that went into this particular map. So we've got a suite of covariates that are being used in the modelling process. They're environmental, they're precipitation, that kind of thing, elevation. They're also socioeconomic, things like poverty are in there. And then Andy's data on population density that we heard a little bit about earlier is also in there. So of all these predictors that are going into the modelling process, you can see the ones which have the highest relative influence on the output, which is the probability of occurrence of this disease. You can also click and get hold of the data that describes the relationship across the range of those covariate values, what's the impact they're having, the relative impact they're having on the model output. At the moment, you can simply get hold of the data and plot that yourselves. We will provide the functionality so that you'll be able to visualize those plots online in the future. So that's what you get. A little bit, some points to note, some bits of caution, and just to make you aware about exactly what we're providing here. So the most important point to note is that our aim has always been to provide the best possible contemporary map we can at the time that the map is produced. And so that has a few connotations. So start with diseases with a lower reporting rate. We'll have to go back further in time to be able to produce a robust map and have enough data for those. And so they will be less contemporary. We'll always make them as contemporary as we can, and there's a balance that we have to achieve there. Even more importantly, it's important to note, and it may not be immediately obvious, that because we always want to produce the best possible map now, that means we're using the best available data that's available now. We're not worrying about what was available last time or the time before. We want to use the best suite of covariate data available now. So at the moment, our covariate data doesn't include anything on vaccine coverage. For some diseases, the map will be improved if we obtain that data and add that in. Also, we have a number of people who are in this room and in the group who are working on improving the model. So we may use new models or new model versions in the future, and the system allows you to change the model that you're using for a particular disease. We will always use the best possible model or model version for the disease that's available at this point in time. So what this means is that the map is as good and as robust as it can be, the one we're producing now, but the set of maps that I just showed you for dengue, the last 4, are not a time series. So if you wanted to produce a time series, you could. All the information is available, the data, the models and so on, they're available, and you could, at this point in time, go backwards and recreate the historic maps. But that's not what we're doing. So it's one approach, but what we wanted to do for surveillance was always produce the best possible map. So that's a very important point to note. One other point to note is I have mentioned that we are providing you with information on spatial variation in the probability of occurrence of human infections. And our group, quite a few of you know already, and we've seen some of the maps already, produce maps that show spatial variation in prevalence or incidence. We also have maps that look at the probability of occurrence of a zoonotic transmission event, which is different to the human infections generally. So that's talking about those index cases before human-to-human transmission starts. So it's important to be clear what's shown with these particular maps on this site, and ultimately the online atlas will have links through in different sections for those other types of map, but we will always keep them clearly separate and segregated, because how you use them and what they're showing are rather different things. Then the final point that I'd like to make, I've talked a little bit about the novel data that we use in this process and the novel methods that we've built to handle that data. That doesn't mean we've thrown all of the traditional gold standard high quality data out the window. This system does have the capacity to receive data from the more traditional sources. So we have some of those ourselves. There may be people in the room and elsewhere who have data they can share, and we have the facility to receive that in a very simple and easy way. And we can treat that data in one of 2 ways. We can treat it as something that has been thoroughly checked, use gold standard diagnostics is very good, and it goes straight through into the model. Or we can treat it as data that hasn't yet been checked and goes through our validation system. So I'm going to finish up now with some links and some acknowledgements. So the site is all up, and if anyone would like to go there and register, explore, please do. And on the bottom here we have the team of people who built this particular site. Thank you.
Any questions for Catherine?
Hi, thanks. It was a fantastic talk. An amazing looking tool. Can you just tell me a little bit about how, you talked about sample bias. Is there any sort of bias with the validation, the amount of information that goes into validating particular areas that shows through in the uncertainty that you get in the final maps?
Well, that's an interesting question. So at the moment, on the validation side, we don't have the data to answer that question. So far, we've been live for 4 weeks, and we've only just told people now, really, that this site's available. So the validations in there at the moment come from our internal group. And to explore that properly, we need validations from out there in the world. So what we're planning to do is come back to this in 6 months' time. So far, we've done all our analysis on the validation using dengue and using our internal group of validators. So we're going to come back and revisit that question in 6 months' time when we have more diseases and more people around the world. And we may actually update our system at that stage as well.
I'm just curious about how much machine learning technique improved. So essentially, what I want to know is how much is the false positive at first stage? Then you have a crowdsourcing type of like an expert opinion. And then you also feedback to the root of training data more by machine learning. So is that going to be eventually you can avoid crowdsourcing, or it's still necessary, or how much machine learning technique can contribute in the refinement process?
So that's a very good point. So we never allow the machine learning system to completely take over. We always want those disease experts validating points, because the behaviour of the disease may change and the machine learning system won't pick that up on its own. So it's got those metrics of the probability of occurrence in that location, so the sort of environmental suitability of that location for the disease, and it knows about the distance from the disease extent, and it may be for months or years those two things don't change, but when they do change, the only way that will be picked up is by the experts. And so we continually need the experts to be providing new training data sets, and every week the machine learning system is retrained. Not only that, we need to take data across the board for those 3 values. We need data across the board for those 3 values going through to the experts and into the training data set. So the training data set covers the full range of values available. Not only that, in addition to us sending data across the board to the disease experts, we actually gear this slightly. So if I have time, I do have another slide on just that question. So we always want the disease experts to be providing their opinion, and there are some types of data that are slightly more interesting for the experts to consider than others. So here on the x-axis are plotted out the probability of occurrence at that environment where the disease point is located, from low to high. And then I've also plotted out on the y-axis the points, how the distance they fall outside or within the current disease extent. And you get a lot of data come in that falls in this top right quadrant. And so this is data that's falling within the current extent and in the environments that the model is already predicting. So this data won't have a huge influence on the map. It will reinforce what the model is already doing. And so this data is slightly less interesting to us. So some of it will always go through to the disease experts because they need to see a full range of data. But we've geared the system so more of this goes to the machine learning process. But we've also geared it that the other types, slightly more of those, go through to the disease experts because they're really interesting. So in this quadrant here, in the top left, for example, these are areas that are in the current disease extent, but the environment they're falling in, we're currently predicting a low probability of occurrence. So if those points are valid, either our model could be improved or the disease is changing. So that's of particular interest to us. Equally, this quadrant here in the bottom right, these are locations where the area we're predicting a high probability of occurrence, but at the moment it's outside of the current extent. So either our current extent could be improved or the disease is changing, and in either instance we're really interested in those points. So we're slightly gearing the system so that disease experts receive more of those more interesting data points. So we always want input, but machine learning will bring the numbers down, especially of these, and a lot of data falls in there.
It's a fantastic piece of work. I know it's early days, but where do you think in the system there are the biggest gains to be made in terms of kind of work now? You know, is it data sources? Is it sort of going beyond logistic regression into more sophisticated machine learning algorithms? You know, is it the experts? Do you need more experts? You know, where are the biggest gains?
Yeah.
You know, I know you're going to need to build systems. But,
Well, no, there are two obvious ones already. So we started with dengue for a good reason, and that's because there's a lot of data in internet reports on dengue. So there are other diseases where the text processing algorithms can be improved, and we want to look at the natural language processes that you can use to obtain data from the internet. And we want to use that partly to increase volumes of data for some diseases, but more importantly to improve the precision of that data, because at the moment we're losing some precision. So we're getting data, but it could be more precise. So dengue is straightforward. I mentioned we've got New World cutaneous leishmaniasis. At the moment, a lot of data coming through is simply defined as leishmaniasis, and that's less informative than cutaneous leishmaniasis, for example. Or we might have data linked to Texas that could actually be linked to a town in Texas, and more geographically precise. So there are some big wins, I think, there on that side of things. Also, we're always, in our group generally, developing those models, and some big improvements can be made there, and we have some of the people doing that in the room. And so I mentioned, and one of the questioners mentioned briefly, some issues of sample bias. So how we handle sample bias and generate the kind of absence information that the models currently need, or whether they'll need them in the future. There are some big gains there too.
Hi, thank you. That's an excellent and really exciting presentation. Has there been any thought to how this data might be used in the communication of health risks for a travelling population, given that there's clearly an overlap between the output from ABRAID and other travel health organisations?
Yeah, so definitely there are huge gains to be had on the maps available for travelling populations. If you look at what's produced by the WHO or CDC or Gideon, there are quite big differences amongst them. So some very simple things in our process for defining your disease extent, even if you're going just down to that level rather than the fine scale map, I think can provide some very useful information, especially if travellers are going to multiple locations anyway. So there are some big wins there. It also comes back to the point about you need to be careful in remembering what we're showing in this map. And so, for example, some diseases are vaccine preventable, and so your risks are going to be different if you're vaccinated, if you're not, and so on. But yeah, definitely there's a huge room for improvement, and this could certainly be used as a resource for that.
I was just thinking about that outliner in Rio de Janeiro state with the climax malaria in the last couple of weeks. That's a clear example.
Yeah.
So, I think I'm going to let Catherine off the hook there, as I can't see any more arms. And say thank you to Andy and Catherine.